Okay, so let's start this session. So good morning, good afternoon, and good evening, everyone, wherever you may be. It is an honor for me to welcome you to this webinar titled of the role of hydraulic modeling in the design and safety of hydroelectric power plants. This is event, it's a joint initiative between two young professionals network, Venezuela and Portugal. It is an effort that originated from the synergy and collaboration between these two organizations. So the idea for this webinar arose from the shared desire of both young professionals network teams to create a space where experts can, in hydraulic engineering, of course, could share their knowledge and their experiences. We firmly believe that the hydraulic modeling is essential for the efficient design and operational safety of the hydroelectric power plants, and we aim to highlight its importance during this event. We are deeply grateful to our distinguished speakers for being here today and to all of you that are participating. We hope this webinar will not only be informative, but also inspiring, and that will foster new ideas and collaborations in the future. Thank you all for being here. I invite all the participants to leave any questions by writing them in the Q&A box in the bottom of the Zoom. And that in the end of the two sessions, I will read them for you. Without further delay, let's begin our first session, beginning with Arturo Marcano. He is civil engineering, majoring in hydraulics at the Central University of Venezuela. He was the past head of hydraulics department and laboratory of EDELCA, where he participated in design and investigation using hydraulic models applied to a number of large hydraulic structures in the lower Caroni hydropower, and he's a member of the Hydraulic for Dams Committee and has participated as collaborator of the hydraulic structures section of HIR since '99. He's presently an international consultant, having worked in hydropower projects in Asia, Africa, Central and South America. Also, he's a lecturer in several universities, and he will present the work of Lower Caroni Hydroelectric Development, a modeling case study. So, Arturo, please share with us your knowledge.
Thank you. So, good evening, morning, good afternoon to everyone. It's a pleasure for me to be sharing this information. I thank YPN from Venezuela and Portugal for the invitation. So I'm trying now to share screen. So I would like to ask whether it's been featured correctly. So we can start to have that. So can you see my first cover of my presentation?
Yes, yes.
Okay. So it says within this webinar, the role of hydraulic modeling in design and safety of hydroelectric power plants, I've been invited to present this case of the Lower Caroni hydro development. So I'll try to run. This is very little time for so many things to do for a project that has been on for more than 50 years. So I will talk about this. I'll be briefing on hydropower in Venezuela. Then I talk about the hydropower development, the projects. Then we talk about EDELCA. It's who run this company. It's a government company who run the development of the Caroni and also motivated and promoted a large hydraulic laboratory to do and perform all kinds of studies during this 35 years of execution of this project. Then some incidents, investigation and solution, and then a final remark. So I'll start. This is mostly well known for most of you. We have 26% of water of the whole planet concentrated in South America. This is a continent of water. It's water everywhere, although there are very few spaces with no rain at all falls. This is in the Andes, very close to Chile. In this here, we can see all these kind of large rivers I have collected from some data. Many of you will be familiar to some of them because of your remote, say, location now. We can see that, for instance, we have Orinoco River is in Venezuela, river basin, but it's probably one of the most best producers of water. I have included here Caroni River, which is not in the same ranking of all these this large river basin, but you can see also a very large production of water of this river basin. Then the hydrograph of the Caroni, we gotta refer to this river, all the development we have done so far in a cascade. And you see here the hydrograph, the maximum around 18,000 cubic meter per second, the maximum inflowing into Guri Reservoir. Then this is also very interesting, is the Orinoco River. It's the third largest river in flow in the planet. So why Orinoco is in display? Well, this is because it is controlling water in the downstream dam to the is the end of the cascade. Is going to control water there. It's going to control the performance of the structure. So it's very important because downstream at the very end, when Orinoco is the city of Ciudad Guayana. This is a city of 1 million inhabitants, with some of them at risk in the floodplain of the Orinoco and Caroni rivers. This is very short about hydropower in Venezuela. We have only 9 hydropower stations. We have 5 in the Andean regions, and then we have 4 in the Caroni River. That's southeast. We have these 3 of Venezuela. It's a small country, but it has a lot of energy. May say hydro production. In this case, about 80% of the whole country electricity depends on the Caroni River basin of the Caroni. We see the 4 or in the upper Caroni for the future. Here the cascade of the lower Caroni, starting with the regulation dam of Guri, 170 meters, and this is a very large volume. It's multi-annual regulation, and finish with Macagua. This is a small development, but still most of them are very productive in energy. Here we can visualize some of the challenges of building all these development when the others are operating, then also having flood control in one or the other. So how to control the Orinoco River, not to affect flooding of releases from Macagua, etc. So we can start to visualize the challenges of this development. Here, the data of the dams in the lower Caroni, we have 6 projects, Macagua 1, Guri 1, Guri 2, Macagua the second, Caroachi and Tocoma. Altogether, it goes over 80,000 megawatts. We have spillways of 30,000 cubic meter per second and 28,600 cubic meter per second. So units, well, of the different kind, to around 60 units to produce all energy. So we start first project. That was Guri the first. These are challenges for this. Well, flow is always a challenge. 40,000 cubic meter per second, the spillway design, diversion 17,000 cubic meter per second. the Caroni uncontrolled, relatively small area of the reservoir, and very interesting, and we had unprecedented hydraulic condition for a sluice closure. We had a sluice closure here in most of these dams, so we're going to see that in some detail. Handling a spillway flow with a very large flow capacity, talking about 40,000 cubic meters per second. This is about energy dissipation, and this had to be seen with a very poor, say, not poor, but reduced capacity of regulation. Not only we have these flows, but we have the spillway operating for more than 60, I say 6 months, 8 months, a year, because the dam was not completed and the flow regulation was not to 100%. Next project is Guri, the final stage. That means to build one dam on top of the existing one and stage one. So the challenge is second powerhouse, tail raise channel is being excavated. And what is the meaning of raising the spillway and the dams, the existing dam, in 55 meters? So in this, we incorporated all kind of problems. We had the Guri one. We tried to solve it, and we tried to include it in the second stage. So we're going to see some of these challenges and how we solve it in a few minutes. So we start to see also that we guarantee operation of this dam while we start to build other development downstream. Just to tell you, to give you some degree of challenge, we build the spillway, we raise the spillway in different stages. And at the same time, we should keep in the structure enough capacity. So it was pouring concrete in one side with gates, and in the other spillway was another level with gates and another level. So river floods will come and had to be released from the reservoir. Here you see also a dam, what is building the dam 55 meters. So this is we just passed that. This is how it looks now. It's something a friend of mine sent me. This is an advertisement from Water Power and Dam Construction. And I don't know the date, but it has very interesting data. And it says at the end that Guri was for many years the largest hydropower station in the planet. So let's go to the second project. This is the further downstream. It's called Macagua. Macagua is a 2,000, about 300,000 megawatts. So, but one thing, one challenge is it's inside a city. So it's an urban project. And the other challenge is it's in a very touristic area where a park, a very well-known park is there. It's a lot of element of ecology in this project. So being also the last project very close to the Orinoco River. So there was some risk and some, say, challenges that may arise for having, say, controlling the water all outflow in Macau. So same thing, we have a construction in one dam. We have to close the full river, Caroni River, downstream, but we should keep Guri operating as it was transparent for the energy, say, supply of the country. Next project is Carhuachi. Carhuachi is in the middle of the two. But what the challenges are, well, Carhuachi, we had to design a spillway, very particular one, to promote diversion, to improve diversion difficulty. So it was a very nice opportunity to test some breast spillways, surface spillway. So we finish up with the spillway work. I got to say relate some studies, say in a few minutes. So again, we had to have also a river closure in the sluice and in the river of, say, some with not much difficulty. So again, Caravaggio is in the middle of the two projects. So handling flow from Guri and retaining in Caravaggio, releasing in Caravaggio or to Macagua, which also may impact the production. So these are the challenges. Finally, this is the first, say, the closest to Guri. It's very close. Actually, you step in Guri Dam and you see the other dam is only 14 kilometers downstream. And challenges are related to safety. Of course, when opening the gates at Guri, and gates in Tacoma project should be also open, etc. So again, we have to confirm all, say, studies, investigation for sluice closure, and also how to deal with the 14,000 cubic meter per second and construction flood. So this company, Adelca, who was in charge of this development, was also has a program, master plan, and decided to have its own laboratory. So it's kind of a laboratory to participate in all this study. So we had our first, say, test 1977. I had the opportunity to participate as a very young engineer, very just graduated from university. So I went to start, I started that experience, and that continued. And even the laboratory, although it's somehow inactive now, it went on for more than 35 years. So I had the opportunity of test and study and design most of the hydraulic structures related to this project. So this is just a strategic location of the hydraulics department where the laboratory was. This is more or less how the hydraulics and department engineering worked out with the design, with the numerical modeling, with the field monitoring, model construction, instrumentation, and also at the end, we run a laboratory. So this is a first setup, first site, our laboratory. We see the large models. All the models of the development was there. We had about these large models. Most of them are over 1,000 square meters. We have facility to test tunnels. We have, of course, a workshop and instrumentation room, and some area for expansion for future projects. So talking about numerical, say, help, numerical support, we use very well known and common software like HEC RAS, HEC-RAS. We managed to measure in a whole 100 kilometer reach, a lot of flows and water levels and so on. So we could see that this model worked perfectly, and our estimation of what was going to forecast, whatever, run very well. This is, we use also unsteady flow, particularly for some situations. For instance, in the Caroni, we have all this sluice closure, and that model would perform very well. Also, dam break we use to do inundation maps. We have this 2D horizontal phase SMS flow. Is very nice also. You can, when we see this model, in our laboratory, we have the opportunity of mixing them and checking one with the other. So that's the kind of thing you can do when you own your own laboratory and your own people to design a project. So we were a team that stayed there for many years. So somehow all this model, although they may look very simple, they were very well, they were very useful. This is another model we used one time. We were dealing with aeration at Guri with this model. Since one lead final element was perfect for the job we were doing at the moment. And we managed to combine this with the prototype and model data, physical model data, to obtain our best results. Then also CFD, that is mostly very common now. That was studies of 20 years, 10 years ago. But it's very interesting. We mix also with numerical, with physical model, 3D. So it was a kind of very nice combination that you obtain to optimize your project. Here's just say a presentation of how many or what kind of model we use for Carwachi. And we have all sort of models we can use about to solve the problem, the different problems we did on that project. Let's talk about some incidents. Then a sluice closure. This is goody. That happened many years ago, but it was a very well-known case. We had gates got stuck and the river could not be stopped passing through 14 sluices. It was designed for 17,000 cubic meters per second. So what happened there? They don't test gates. They didn't do it. They were, they thought they didn't need to do it. The design was not very friendly either to close with some additional things. There was not second slot. That means no an emergency closure. This is what I'll mention to you later. It's very interesting. Then they did many things, but none of them worked. So they finish up with this kind of arrangement. They are falling heavy things until those were placed in front of the sluices. They were closing one by one. And it was a nasty situation. It lasted for some time, but they managed to finish. Somehow that lesson was in our minds, although we were not at that time in the place. Let's see how we saw this in Carwachi. So in Carwachi, we had the laboratory. We have people there, we have engineers. We could analyze first the kind of spillway. We needed to have 14,000 cubic meters, 13,000 cubic meters per second diversion and 30,000 cubic meters per second as a service spillway. So we managed to finish with this structure, which has been built now and is operating. We had two slots. We have possibility of have a service closure downstream, and we have possibility to have an emergency close. So it was 18 sluices, 1525 times 22 meters, sorry, 9 times 55 meters. But we implemented some modeling of gates. We had our own model, and the contractor was contractually had the obligation of doing another model. So we found all kind of data. We needed to design cranes and with these models. And eventually we finish up with this project and closing these 18 sluices rather smoothly, we will say. In this graph you see here, you see how we managed to close them step by step. We use full equation and steady flow to simulate the different situation we had in the river while making every sluice closure. And here you see spectacular closure of the last sluice with 28 meters of head difference. And of course, after that, acceleration. Then the lessons. We didn't have, we learned that investigation should be done, that provision should be taken for second slow when you have this kind of situations at the river, other protective measures or a provision, still lining, etc. So we feel that was also a very good idea. We had the laboratory, we had the people there, we have the intention of making not repeating the same failure. And actually, we use the same equipment to close 10 years after the sluices of the Tacoma project with no problem at all. So we go to another incident. It's also Guri. Everything comes from Guri. It was so monumental. It was so daring work. It was a time of things should be done that way. So we have these flip buckets there, and we have the sluices. That was so we start having this kind of behavior of flip buckets. They were terribly badly. They were also, we had a lot of things, problems to repair them with this gate that was floating. You know, you can imagine all kind of problems because the river had to be, the flood should be released in the next, say, gates while you were doing the protection. So what was the cause of this? We have very large structures working with submergence, a very complex flow in the, say, in this interface of submergence and flipping. So that was investigated in the large model in San Antonio Falls Hydraulic Laboratory. And a decision was then taken by the company to raise this flip bucket. So we went again to physical modeling, and we finished up with raising these 3 buckets. We did quite a lot of tests. I was one of my, say, jobs, the tasks I had to do, where we tested so many flip buckets, and we finished up, range were pretty good. So the lessons, yeah, I mentioned some of them. Well, design is not, it's very large prototypes. We don't know much about how they're going to perform, and we should take the risk. And eventually, if we had a chance to improve, repair, or to do rehabilitation as we did, that was something that very important we consider. Second incident is about cavitation. Same come from Guri. And we have so many other lessons, some other cases in the other projects, but I think that they're very, say, prominent. Cavitation, there was a lot of cavitation in the first structure. So, of course, at that time, it was popular. It was becoming not so popular, but it was in many surface spillways, large, the technical of aeration was introduced. So what do we do in what we did in Guri? We started to test how these devices will perform. We had the prototype, then we have a large physical model. We count also with sign numerical tools. So we started to do testing in the prototype measurements, and we finished with this kind of arrangement, which is very unique and strange. It can be used, of course, in other projects, but it's an aeration system that you build when you have a project already built, say, put it in that way. So the best possibility was adapt a system of air galleries, as you see there, with some intake somewhere in the close, and then a manifold of air. So that we had the chance of measuring all that. We measured negative pressure, we measured flow, velocity, and we managed to go in, say, developing a method. So at the end, we finished with a couple of aerators in each, say, in each chute, that we have gallery in the downstream aerator, and we have a ramp at the end of the pier. So they will perform very well, and we finish this. For instance, these 2 graphics, they come from prototype measurements, and from that we can estimate air concentration of about 50% that are the one we asked in the design to protect the spillway surface. So I think we're running out of time, so I have more topics, but I will finish my talk with with some final remarks, I would say there is some confidence that created to have this laboratory performing, well equipped, and very motivated with this project. The laboratory actually was next to the works. We could go to any of this work in less than 1 hour. We could move there and see the structure performing. We could go for meetings there. We could inspect the job done by contractors. So in that environment of, say, total control of what was going on, we're always also part of the design team, as I mentioned earlier. So this is a key for success. I think we didn't lose the respect to that such a large river. We had a lot of surprises from it, but we were capable of handling them, of facing them, always with the help of our mentors, of more experienced engineers, more experienced experts that always were around us. So I think that it's my last word. I would be very happy to answer some questions. It's a pity, no more time to give more cases, but well, we may have another opportunity. So thank you very much for your attention, and I'll be willing to answer any questions from you. Thank you.
Okay, thank you, Professor Arturo, for the presentation and for keeping the time. Let's leave the questions at the Q&A, okay? And I will do them on the end of the session. So now let's go for our session number 2. And the presenters are Sílvia Amaral and António Muralha. Sílvia holds a PhD. She is currently an assistant researcher at the Portuguese National Laboratory of Civil Engineering, where she has been since 2006. She has also an extensive background in hydraulic engineering and is specialized in hydraulic structures, fluvial hydraulics, and water resources. Also, since 2022, she has also collaborated as an invited assistant professor in a university here in Lisbon, where she lectures the subjects of general hydraulics and hydrology and water resources. Regarding our another presenter, António Muralha, is also a civil engineering, a master's from University of Lisbon. He started his professional journey in 2000 at LUNEC, where he worked as a research fellow. And during this tenure, contributed to various research projects he conducted at LUNEC's experimental facilities. At the moment, he's a PhD candidate working on high-velocity water jets, combined CFD and experimental approaches to characterize the scarring process, with LUNEC as a host institution. And also, he's since 2020, he's a senior technician positions at LNAC, where he continues contributing to ongoing projects while pursuing his PhD research. So let's start. Thank you.
Okay, thank you. I will start to... vou tentar partilhar aqui a apresentação, não é? Achas que é melhor aí? Partilhar aqui... Como é que eu faço isto? Share screen, não é? E vou fazer este próprio. Este? Ok. Mas isso será que isto agora fica em modo... Espera. Ai, meu Deus. Cada atrapalhada aqui. Ok, sim. E aqui. Espera só um bocadinho. Just a second, ok?
Don't worry, take your time.
Prefiro assim. Are you seeing the entire screen?
Yes, we see the entire screen. It's perfectly fine.
Okay, so we have the airport right next to us, so sometimes I will see the need to stop, so that the planes can pass and you are able to hear us. So, good morning and afternoon and evening for those wherever you are, I don't know. I am Sílvia and António is next to me. We work at the National Laboratory for Civil Engineering in Portugal, and we are about to present you the role of physical modeling in studying large hydraulic structures and deepening phenomenological knowledge in scientific studies. So, we will split the presentation. I will start and then António will present the technical part of our presentation. So just to give you a framework of the presentation, we will start to give you an overview of what is the Portuguese National Laboratory for Civil Engineering here in Portugal and what is the main goals of this lab. Then we will show you the hydraulics and environment department, which is where we work, and our particular unit, which is the water resources and hydraulic structures, where the physical models are conducted here at LNEC, the physical models, of course, of hydraulic structures. So then I will offer an historical framework or background of what is and what has been the physical modeling of hydraulic structures, as well as some examples of some reference studies performed here at LNEC across time will be given. Also, a view on the evolution, not only in the construction methods, but also in what concerns the data acquisition technologies, as well as the novel post-processing methods that are currently being applied, will be also presented, as well has some final considerations that we'll perform at the end. So, for a start, LNEC, the National Laboratory for Civil Engineering, is a state laboratory that dates from 1946, which meaning that it has almost 80 years. It has actually started with the hydraulics department, with the physical modeling subject. So it operates in several fields of activity, being its main fields, the civil engineering works directly applied to public works, since it is a state laboratory, housing and urban planning, also the environmental concerns, the building industry, and last, the components and other construction products. So LNEC works mainly for society, trying to give answers and to improve the society as a whole in terms of public works. So I think we are proud to inform and to tell that LNEC, with these 80 years of almost experience, have been able to perform studies, research projects, consultancies, courses, formations all around the world, currently in more than 50 countries and in all 5 continents, being in this slide the representation of some of these locations. So our department, the Hydraulics and Environment Department, is a wide scope. We are only a unit of these departments, but in general, we are, or we can say we are divided in these 5 areas, being the first one, the urban waters, more currently called the sanitary engineering, the estuary and coastal zones, the harbors and maritime structures, the water resources and hydraulic structures, and the groundwater. Well, these physical model studies applied to hydraulic structures are performed mainly in the water resources and hydraulic structures unit. This unit is where me and António are from, and we perform many types of studies, among which research and development studies, applied investigation studies, but also consultative projects that are meant to give direct answers to specific projects, mainly in hydraulic structures, in rivers, aquifer systems, all integrated at the river basin scale. So here in this slide, some examples of our facilities, of our flood studies, of our physical models, as well as of our numerical simulations. So, in terms of our competencies or our tools, we can mention that we act at 4 different fronts. Being to say that it would be at the laboratory front, a field front, at a computational front, and at a decision support front. So in what concerns the scale, the laboratory front, we have our scale models, which are mostly physical models that can be divided in 2 different activities. Physical model applied to give answer to certain specific projects, mainly that are being constructed or that have to be improved. For example, power plants that are performing some power reinforcement. This is just an example. In terms and also at the specific investigation studies that most of the time gives origin to PhD studies, or lines of research that we have open and that are of most absolute interest here at LANEC. Then we have the field monitoring. There is composed by some field campaigns and sensors installation at the prototype scale that are monitored, and where we gather data sometimes to compare to our physical models data, but not only. Then we have the computational part where we also act, which is composed by the numerical models. And in here, of course, we do not have just one type of modeling. We have this specific CFD modeling that we are currently performing with OpenFOAM, I believe. But to simulate, to do this combined modulation with the physical models. We do it also at the numerical scale, but also some fluid propagation studies that we do by using EC, RAS, Mach 11, or some other types of fluid propagation softwares. Then we have these decision support systems, which are mostly platforms that were created where we give informations to support the decisions. So some examples of our facilities and of the flood propagation studies. So regarding the NERE as a whole, I can state that currently the advances we have nowadays in what concerns the construction of scale models, namely by using these novel approaches of 3D printing, computer, the control of equipment by automatically by computing. Even the new materials that we are able to use, combined with the integrated modeling of complex geometries of hydraulic structures, not only with physical modeling, but also with CFD simulations, allow us to affirm that we are currently at a stage of strong improvement on the characterization of flow behavior around hydraulic structures. There is to say, not only, but also spillways, hydraulic circuits, and other specific hydraulic structures. I think I should make a remark in here that we mostly refer to the spillways and hydraulic circuits because plenty of our work, of our consultancy work is concerned with dams, with the hydroelectric power plants that are already built and being improved, or that are about to be built. That's why this is a huge part of our work here at NERE. So I can say that NERE, from this point of view, performs an important activity at the national and international level. So you have here the example of a physical model, on the right side, a numerical model, and below you have also the sensorization, the sensors installation at a prototype scale. Of course, this is not always possible, but in some models that we have accompanied from the start, during the construction of the dam that follows the physical model and the numerical model, we were able to install some sensors in order to compare with our results. So in terms of lab facilities, there are plenty here at not only in RE, but in DHA, in the hydraulics department as a whole. We have a 5,000 square meters indoor area with a pumping capacity of 500 liters per second. So we count with an artificial aquifer where we are able to perform pollutant tests for groundwaters, with a channel that allow us to perform reservoir sedimentation by studying the turbidity currents, a facility where we study the jets impacts on a
plate or a sealing basin.
On a sealing basin, which is actually the field of the PhD of Antonio, which is about to finish. We have also a non-conventional spillways facility where we study precisely the aeration issues, sealing basins. We also perform at a scale of embankments, like the failure of embankments, in this case river dikes or even embankment dams, fish ladders, flumes with variable inclinations, where we are able to study the scouring in bridge around piers, steep spillways where the aeration is also an issue, water quality and soil laboratories, as well as the study of floods in compounds channels. Of course, these are not all our facilities or our flumes or channels, but it gives a good idea of what the kind of works we perform in here in terms of physical modeling. So, generally speaking, what is this physical modeling? So, this involves creating small-scale physical models to study and predict the corresponding flow behavior under several operational and environmental conditions. And of course, these physical models are essential, are absolutely crucial for the planning, design, and operation of dams, in our case, which is most of our work, hydroelectric power plants, and also associated infrastructures. From the role of these studies point of view, we can say that physical modeling is very, very important from the design and planning of a project. I mean, the validation and optimization of the design of the dam that was initially sought and dimension based in the theory. It is also essential for the hydraulic analysis in terms of how the flow behaves near the hydraulic structures. Also fundamental for the safety and reliability of the project, being that it allows, the physical modeling allows to identify potential structural or functional failures, and also to perform the studies of erosions, downstream dams in rivers. Also allows for mitigating the environmental impacts, as it adds on identifying any negative environmental impacts. This is particularly true when we talk about fish ladders, for instance, where we can try to understand which alteration will be implemented on the aquatic habitats and water quality. As a whole, we can say that physical model acts as a whole operational optimization, since it enables to optimize the hydraulic circuits as a whole and the reservoir management. So, just some final remarks before I pass the word to Antonio. I should say that at the beginning of the 20th century, the first physical models or the first studies on these hydraulic structure, we should say, were mostly based on empirical models, and the reduced scale models that existed, if they existed, were very, very simple, made with very simple materials as wood and concrete. Later developments around between 50s and the 70s, some novel technologies started to appear and it started to build models with a higher precision. These were the decades where the first computing methods started to appear and to give a little help on these studies. But it was only after the 80s and between the 80s and 2000 at what we call the digital age that some strong improvements started to be seen through the starting of using the computational modeling and starting to give a bit of help to define the physical models. And we started to use some more sophisticated instrumentation, not so sophisticated nowadays, but at that time was really different. And after 2000 up to the present, we are at a scenario of a complete integration of the physical modeling with the numerical simulations, most of the time by using computational fluid dynamics, the CFD, also using the augmented reality and 3D simulation. And we can also say that besides this, there has been seen a strong increase on the focus of these physical models, not only on improving the forms and the design of the structures, but also on creating projects that are sustainable and resilient from the environmental impact point of view, and by adding the climate change and extreme events in the simulation. So now I will pass the word to Antonio.
Thank you. Now I will present 4 different examples we have here at LNEC. We identify 4 different physical models we built here from the past to more or less nowadays. First, only for indication, and because it is from Venezuela, we built in the 60s a physical dam of the spillway of El Diluvio Dam in Venezuela. We built 2 physical models, one 2D one of the spillway on the scale of 1 to 100, and the other one a normal model, let's say a 3D one on the scale of 1 to 50, with the huge dimensions for not compared to the 2D model. And in these photos, very old ones, it's possible to identify the old model, the upstream control section of the spillway, and the downstream view of the spillway. Here is 2 photos of the spillway discharging the normal design flood, and at that time in our physical models. Passing to more recent models, here is one from Spain, is Undurraga Dam in the north part of Spain, and the main objective of the study was to study how it will be possible to increase the capacity of the spillway. Undurraga Dam has one existing spillway at the top of the dam, the main spillway, and another one was projected, the auxiliary spillway. This one is the main objective of this study. We built a 3D physical model, and in these photos is possible to see a downstream view of the jets created by each one of the 2 spillways, with 2 spanks each one, and the inlet structures of the of the spillways also. In this case, we found some problems present here in the figure of the right. We found vertical vortex in the inlet structure, causing some problems because the flow inside this spillway is a pressurized flow by a siphon. And we make some changes in our physical models to trying to, with the main objective of eliminate this type of structures. We built several alternative solutions, let's say, in wood at this time, with forming a grid, and we found very good results in the flow conditions after the test. And we proposed to our clients some changes in the initial design in order to eliminate that vortex that occurs in the physical models. Passing to Portugal, Caniçada Dam is a dam already built in Portugal in the 50s, in the north part of Portugal, with an existing spillway at the top, with a maximum capacity of 1,700 cubic meters per second. And during to the new regulations and to the revised climate data, a new spillway, a complementary one, was built with almost the same capacity of the existing one. We built a physical model here with complaining the existing spillway, the complementary spillway, the upstream reservoir, and the downstream strength of the river. We study here. I will focus only on the ski jump structures of this complementary spillway. We study the design shapes we have, and we found a very compact jet in the figure in the left, and it will cause some erosion at the river bank. We study 8 types of alternatives, like the figure in the right side, with the wood simulating different configurations at this time. Nowadays, we don't use wood too many times to do things like that. After that 8 iterations, we found with our clients a good agreement in the solution for the ski jump structure, and we found less erosion, a more dispersed jets in the air, a more dissipation of energy in the air and through the atmosphere, and is better for our clients. Now, Alto Tâmega Dam is the let's say the last dam we built here in Portugal, is finished this winter, and is also in the north part of Portugal. It has 2 spillways, one in each bank of the river, and we built the model on a scale of 1:46. The dam also have a power plant at the bottom of the dam, and like the same, we built all some part of the reservoir and the river downstream of the spillways in this case. First, we studied the right spillway, and more or less the same procedure. We found some compact jets in the beginning, impinging in the left bank of the river. It will and causing severe scour problems. Then we make some changes. We propose new structures, and in the right figure, is possible to see a more dispersed jet in the atmosphere, traveling more time in the air, dissipating more energy, and after all, reducing the scour at the physical model. For the other spillway, the spillway on the left over the left abutment of the dam is more or less the same procedure. We study the ski jump in the preliminary design shapes. Is a very compact jet impinging at the bottom of the bank of the right spillway, can cause problems due to scour in these hydraulic structures, and we make some changes, and the proposed structures reveal a more dissipated jet in the air, more impinging at the river central line, and creating less erosions. In this model, we use photogrammetry to characterize the scour of the jets of the spillways at the bottom of the river. Here are the results of the operation separately from both spillways. Now let's talk a little bit about the evolution of the construction methods in the physical models across the time. In the past, we built physical models like it is present in these photographs, with masonry walls, with bricks, with sand, with the gravel, and with lots of work, lots of effort, consuming lots of time. And it was difficult to build, difficult to destroy, difficult to maintain, and difficult to implement some changes. Nowadays, we are not able anymore to produce, let's say, models at this with these traditional or old constructive methods because of the deadlines of the projects and because of the needs of the resources in terms of operational personnel. Now we are trying to use novel constructive methods like 3D printing. Here is possible to see on the left figure the structure of Alto Tâmega, one of the spillways of Alto Tâmega Dam, when we start to introduce 3D pieces of to modify the ski jump structure, and in the right figure, 3D piece of an experimental test of a dam failure in one of the flumes we have. Now we abandon the old traditional way, and we start also cutting acrylic plates in a computed automatic machine to build lighter models, more clear to see the water inside, and easy to build, easy to destroy, less time consuming, and easy to change if it is necessary. Now, one of the last models we have here, we cut all the pieces from the model more or less in our CNC machine. We PVC plates. We make a big structure to support the model, and it's lighter. It's less time consuming. It's easy to build, easy to demolish after the model was the study was completed, and our clients also are also have the results faster because it is faster to build it. Here is a small video, a small time lapse about how a model like this we built. We start to make some reservoir, putting some styrofoam plates, automatic cut to represent the terrain, some cement pasts also to impermeabilize the terrain and join all the pieces together, putting some PVC pieces to make the shape of, in this case, a steel embasing, and finalizing it with small pieces of a fish passage here at the bottom left. The main objective of the study, produced by automatic cutting machines and 3D printing. Almost finished, and then water are starting more or less to fill the reservoir, and in the next seconds we have water in the model. Of course, with some leakage because it is a laboratory, it is a facility, and we have to deal with these small things all the time. Now the evolution of the acquisition technologies we use in the data acquisition. Let's focus. We acquired lots of variables. We measure lots of things, but let's focus on two of them. A 3D representation of the scour of dikes and dam breaks. We use photogrammetry, cameras with deep sensors and laser scannings, and the characterization of the velocity fields in the same type of structures. We use high velocity cameras, and we perform particle image velocimetry and particle tracking velocimetry. Now let's pass to Sílvia again.
So we are almost reaching the end. So some final remarks about the importance of physical modeling of large hydraulic structures. Just to finish, I have to say that, as I referred at the beginning, the physical modeling, we can say, started in the early 20th century. And at that early stage, the focus was essentially on design verification, and this was performed with some basic methods, and only basic hydraulic analysis was possible at that time because of the limited resources, and the precision was really restricted. Today, we can affirm that the physical modeling has indeed evolved significantly, mostly because of what has been referred, the novel construction methods, the novel materials, even the equipments, the novel technologies and methods that we dispose now to use on our physical tests, but also because we are able to combine this physical modeling to do an integrated analysis on the hydraulic structures, on the flow behavior on hydraulic structures by performing physical modeling and also numerical modeling. So in the future, we believe that large hydraulic structures will points to an even greater integration with the emerging digital technologies, and the emphasis will increasingly be on using sustainable and resilient projects. The climate change will be at the top of the concerns, and the response, the adequate response to extreme events. And also these combined model, these integrated modeling by combining the best of the physical modeling techniques with the best of the digital simulations or the numerical simulations with CFD. And we believe this will be the key to meet the future challenges on this type of studies that will allow to assure safety and efficiency of these large hydraulic structures. So from our point of view, we still believe that the physical modeling of these structures has been and will for sure continue to be essential for the success of these structures, the large hydraulic structures works, and through its evolution from the basic empirical knowledge that we saw at the beginning of the 20th century to the current advanced digital technologies, it will allow to ensure accuracy, safety, and sustainability of infrastructures, and continually be able to adapt to the needs and challenges of the future. So that's all for now, and we thank your attention and also the possibility to present our work. Thank you.
Thank you.
Okay, thank you so much, Sílvia and Antonio, for your nice presentation. Let's move on for our questions now. I have already some of them. I think Professor Arturo is having some internet issues. Let's wait a little bit, don't worry. So maybe we can start with the question from Emilio. By the way, I apologize if I'm not pronouncing your names correctly. Okay, so Emilio has a question. He says there is an excellent presentation, this one from section 2. And he's asking why choose the scale of 446, I think it's Altam Gadam. It is because of to avoid the scale effects or use all head and water supply available in the lab?
In case of Altam Gadam, normally at LNEC, our limitation are the pumping system. We try to build models bigger and bigger in terms of space. It is possible, and if we have the limitation of, we make the calculations of which corresponding to the design discharge in terms of liters per second in our facility, and we make some adjustments. In other case, is 46 point some things because of the hydraulic circuits. The hydraulic circuits the scale of the hydraulic circuit has to match the scale of commercial PVC pipes, and in this case we have the diameters of the PVC pipes are not friendly numbers, let's say the interior diameters.
Okay, thank you, Antonio. That was clarifying. Next question. I think Professor Arturo is okay now. Can you confirm me that, Professor?
Can you listen to me?
Yes, we can hear you. Okay. So you're on again.
I'll try to catch up.
So we have a question also, I think it's for you, from Juan Liscano. He's asking if in this project are the necessary structures contemplated to allow the migration of the fish endemic to these bodies of water?
Okay, this is, thank you very much for the question. It's a very frequent question done to our projects. I actually myself, I made that question quite a few years ago. And according to the water quality of the river,
Are you there, Professor? I don't know if you are listening. Professor, I think, yeah, your micro was not on.
hello?
Hello? Yes?
Now, it's can you hear me now?
Yes, you can hear, we can hear you.
I wonder if my question, my answer was copied there. So we can sum up and say that it was not considered to have ladders for fish, since at that time it was thought that, and actually it's the present situation, fish activity is very small in waters of the Caroni River. So what is being exploded is species of cases where animals are fed artificially. So instead of having fish ladders, is being used very frequently. So my question is snow. We've done quite a lot of say studies and investigations, but it has not been done in any of these projects.
Okay,
Thank you.
thank you. Thank you, Professor. Another question is from our participant, Greg Pedrick. His question, if there are aerators in the Guri passive, or do you have to introduce pumping, flow, etc.?
Okay. Well, artificial natural aeration is artificial, but air is being taken by the flow naturally, say to put it in some way. The aerators, at least the one we had at Guri, should have possibility of introduce the air coming from the air source. So there's always the possibility of having that through the air cavity. So an air cavity, an efficient air cavity should be created. So this kind of suction, what you call pumping, or negative pressure, should allow the air to enter the flow. So at Guri, all that is performing that way. Why we have the atmospheric pressure and the very end of the intake, and this pressure goes lower and lower and lower as air is entering the nape of the flow, the water flow. So the system should be designed in a way that this pressure is kept to some standards, -1, maximum -2 meters of water column. So you can have an efficient way of air entering the flow. So my question is, they are not passive, there's no pumping. It's cavity are forced by flow, and the system structure should have that the geometry, and flow should have the configuration so air can be drawn efficiently into the water flow. I wonder if that's clear.
I think it's clear. Another question, I think this is for both sessions, if it is possible to apply artificial intelligence tools like artificial neural networks and artificial neural fuzzy to model and optimize cultivation damage. This is a question from our participant, Gobuzan.
So, well, maybe I can give a brief answer to that. Well, you don't know where artificially intelligence is going to. So I wonder if there are already some investigations about this. I haven't applied myself, but it should be there, I guess, in the near future. I wonder what can be said from the other panelists.
Yes, I think since we have data of cavitation damages and we can relate it to anything, AI will be able to do some things and to make some correlations maybe we are not seeing right now. But if you have a huge database of data cavitation damages or the conditions with the flow conditions what caused that damage, maybe artificial intelligence will do some correlations and give some answers about the flow patterns at when the damage occurs. At these days, all the innovation is about artificial intelligence. Maybe in the next months, what I am saying now is completely over posted by the evolution of this type of technology, because it is the on a daily basis instead of what we are normally seeing in our investigations. It takes years and years, and the intelligence artificial are growing and growing day by day.
Okay, thank you so much. I think the next question also is for both speakers, and it's from our participant, Greg. He's asking if you ever fly drones equipped with light detection and ranging systems or similar to examine, detail the large hydraulic structures, because he's interested due to the heavy payload at LIDAR can pose, that these advanced can pose.
So I didn't get the question, Solange. Can you?
Yeah, he's asking if
again?
do you ever fly drones equipped with light detection and ranging systems similar to examine the detail of the large hydraulic structures?
Talking about drones in the hydraulic
Yes.
structures. Yeah, it's well, it's another so one word about this. We see drones also more frequently in the measurement inspections. I don't know if the question is about how to inspect hydraulic structures and some damage, or way of visualizing the structures. And question it's yes. I think it's if this is what the question is asking for. As we find more developing on instrumentation on drones, I'm sure we're gonna have more way of reaching all these very complicated structures. Sometimes we don't have even the possibility of looking at them. So that would be my answer from this side of the question. I wonder if I answer, maybe Antonio can add on that.
Yes, here at LNEC, in terms of hydraulic structures, we don't do too much things with drones. But in terms of general dams, in our concrete dam department, they're making regular inspections to dams in all over Portugal, and sometimes they use drones to make some videos and to take some data. In regions it is impossible to access without this type of devices. We are starting to using that. It's a possibility also for hydraulic structures, and we will in the next years try to put drones in hydraulic structures, making some measurements or making some films in order to calibrate or validate numerical models with this data. I hope I answered the question.
Okay, thank you, Professor and Antonio. We have another participant asking why don't designing hydroelectric projects based in head pressure by pipe and not necessarily based in storage as dam?
Well, I didn't get the intention of the question. It's about storage. Why changing storage by pipes, or I'm sorry, didn't get
Yes,
it.
I'm also trying to understand. Let me see what is writing
Storage.
here.
Yeah, I think
I will wait for the participant to ask for the meaning of his question.
okay.
And then we can move forward to the next one. There is a colleague here asking if there are any research gap that needs to be closed in hydraulic structures for performance, like suitables for a PhD research. This is a very good question.
This is for Antonio. Is looking for.
Are you looking for any PhD students?
Well, to give you an honest answer, if the answer would be no, that would mean that all the research subjects would be closed. Of course, that there is always plenty of subjects already on the line to be studied in terms of improvement of spillways, on dissipation basins, on improvement of the performance of hydraulic circuits in terms, for instance, avoiding cavitation. So it is not a dead end. It is the exact opposite. There are plenty of subjects. If you are interested, we can talk later and we can try to find you a very interesting PhD subject.
Thank you. I don't know if Professor Arturo has anything to say about this request.
No. Well, at the moment I am at the university. We don't have any project for PhD at this moment, but there are plenty of places where to apply. I will suggest to get some information from other places where they have a good, say, particularly financing to have PhD students. Yeah, so we cannot offer at the moment, I'm afraid.
Okay, thank you. Another participant, Hazi, has a question about model and prototype conformity. Regarding as we are using in the model small size 2 millimeters of sand for movable beds? Let me-
I don't know. Can I try to make some comments?
Yes, yes, please.
I believe the question is not well posed, but I also I think I understand what he's trying to ask. Well, he's probably concerned how to assure a good match between the model results and how does he passes the model, the physical model results to the prototype scale, considering he has a small scale particles of 2 millimeters sand in the movable bed. What we can say about this is that of course, that when we model hydroelectric power plants, well, the dams, we also model the approach valley and the downstream valley, and most of the times we also model the sediments on the downstream in order to evaluate the scouring and the erosion. But of course, we know that we are working with fluid models in which we don't consider very much the viscosity effects, and we know that not all the scales of the model can be reduced from the prototype to the scale model directly based on these fruit scales, and the sands and the sediments is this case, which meaning that if you wanted to perform a totally correct model, we would have to construct a distorted model with a different horizontal and vertical scale, which is actually not what we usually do. So what we assume is that, of course, we have scale effects. These are particularly important when we work with erosive models, but we try to find this window where the results are extractable to the prototype scale, and we assume that out of this window of results, the results are simply not entirely correct, and we assume that we accept that scale effects and that errors. That is the honest answer.
Okay, thank you, Sylvia. Our last question is from.
I think Professor Arturo Marcano wants to
Oh,
add.
I'm so sorry, Professor.
Yes,
I'm so sorry.
just to add about mobile bed. It's a complex topic. In hydraulic structures, it's done in all laboratories. I actually remember conversations with Professor Martins in LNEC many years ago about energy dissipation, and he's written some procedures to do that. We do that in all laboratories. But as you said, Sylvia, a couple of minutes ago, it's very difficult to correlate with prototype. It's just something we do, and we are in all laboratories doing mixtures of crushed rock with clay or either crushed rock, and we are looking for, say, preliminary comparative studies rather than actual erosion. So it's a matter now probably for engineers dealing with river fluvial to see whether that changes. But hydraulic structure, normally these tests are done in all laboratories, and they are used for design. They are used to compare different alternatives rather than looking for the actual erosion pattern that will occur in the future. That's maybe I can add that. Thank you.
Thank you, Professor. Our last question is a very simple question. Why can we increase the capacity of an existing dam by raising the level of the dam itself?
No. It cannot be that.
If it was that simple.
It is not that simple. Professor, do you want to give a?
No, I didn't. Sorry, I didn't hear properly. Can you say again, Solange? Sorry.
Yes,
How-
yes.
how-
Why can we increase the capacity of an existing dam just by raising the level of the dam itself?
How we increase the
The capacity,
capacity
the storage
without
capacity,
storage, without raising the dam?
by increasing the height of the dam, level of the dam.
Well, I think if I understand that that's been done to increase the head, you can raise the dam as we did in Guri. We raised 55 meters of reservoir. We increased capacity from say 800 millions, 800 hectometer cubic to 3,000. At least, and of course, there was raising. It's a complex procedure. And actually, there is a bulletin in ICAL about raising dam, building a dam on top of the other. And I think there are many examples of dams being raised partially. A couple of meters, 3 meters, 4 meters, just to, well, to guarantee or to improve, or say, water safety. So it's, I think I've seen many reports of that. So it's not something that it's impossible or it's difficult.
Okay, but it's in somehow can create some vulnerabilities on the dam itself, right? By doing that, by performing that. Do you think so, Professor?
You mean vulnerability in which terms? Of course, every work should be analyzed properly, and
For
I'm
sure.
sure in the environmental issue should be treated totally, even if you're going to raise 2 meters or 1.5 meters. It's vulnerability is related to environment, it's related to risk of say hydrologic risk, and so it's well, it's a project that has to be say conveyed properly and treated as the requirements from the regulations asked. So it's but I repeat, it's something we're talking about. The storage is more needed every day. So some countries will have new places to big dams, but some others won't. So they will try to improve the capacity of the existing infrastructure. So I don't think it's something that it's coming very frequently. So I think that's definitely possible.
Okay, thank you, Professor, for clarifying this question.
I just want to add that of course depends on the solution of the dam. Of course, if it is a gravity dam, you just have to increase the top and put some weight on the downstream side, and it is okay. But you have a double curve
Concrete.
concrete arch dam, you will not be able to do so for sure. But if you have an embankment dam, again, you can increase if you are sure that you increment the weight of the dam on the downstream side, for example, to avoid the slipping of the foundation, among other issues. But the gravity dam, indeed, it can be raised, not for the double, of course, but it can be raised. So it depends. The honest answer would be it depends on the solution, of course.
Okay, thank you. I don't think there's any more questions. I just wait like a minute to see if anyone wants to ask anything else. So as a thank you note to the invited speakers, Well, your presentations were outstanding, showing not only the meticulous research and clear insights, but also an engaging delivery that captivated this huge audience from the beginning. And to our participants, thank you for being here in this online webinar and for the questions that you present. They made it a truly productive and enjoyable session. From the Young Professionals Network from Venezuela and Portugal, we appreciate your time and we look forward to see you in the future events. So kind regards. Thank you, Professor Arturo, Professor Sílvia. Thank you, António. And I don't know if anyone wants to say anything. I can close this session.
I think
Thank you
we
very
have
much.
an
Thank you very much.
Thank you.
Thank you, everyone. Have a rest of the excellent day.
Thank you. Bye-bye.